Hi, I am Stefan Shishkin from the Fraunhofer Institute for Digital Media Technology, and today I would like to briefly present our work on a method for active learning for sound event classification using Monte-Carlo Dropout and PANN embeddings. This is a collaboration with Danilo Hollosi from the Fraunhofer IDMT, Professor Simon Doclo from the University of Oldenburg, and Dr. Stefan Goetze from the University of Sheffield. The method we propose in this contribution is DAL, as in dropout-based active learning for sound event classification. The method makes use of PANN embeddings and Monte-Carlo Dropout and outperforms some state-of-the-art methods on the UrbanSound 8K dataset. Let me first provide you with the motivation behind this work and describe the task that we want to solve. Consider the situation where we have a big collection of sound segments, maybe tens of thousands of sound segments, where each segment contains acoustic events of only one type. Let's say each segment contains either dog barks or sounds of a car engine or gunshots. We are given some initial set of labeled segments. We know that each segment belongs to one of the three classes, and our job is to label the rest of the sound segments with the respective class label. We can do this by hand. However, for large collections of sound segments, this is a time-consuming task. In our work, we therefore investigate a machine learning system that learns to classify sound segments from few provided ground truth labels. Unlike in a typical semi-supervised learning setup, where we would train our classifier on the labeled and unlabeled data, we formulate the task as an active learning task. The difference between semi-supervised learning and active learning is that in an active learning setup, the learning system can ask a human annotator to provide additional ground truth labels for a limited number of unlabeled segments. This means that a good active learning algorithm will try to find most interesting, most informative segments and pass those to the human annotator during the learning process. So let's now look at our implementation of the active learning system. There is a set of unlabeled audio segments and a small set of labeled audio segments to start with. There is a human annotator, and the goal is to train a neural network to classify audio segments using as few manual annotations as possible. The active learning algorithm iterates between two phases. In the first phase, it goes through the pool of not manually labeled audio segments. In this pool, the algorithm finds the audio segment where the classifier is most uncertain about its label and passes this segment to the human annotator. I will describe shortly how we find this most informative segment. The human annotator assigns a label to this audio segment and puts it into the pool of manually labeled segments. The algorithm also finds unlabeled segments where the classifier is very certain about the labels. These segments automatically receive so-called pseudo-labels and are copied into the pool of pseudo-labeled segments. In the second phase of the active learning process, the classifier is trained on both the pools of manually as well as pseudo-labeled segments. After that, the algorithm again switches to the first phase, goes through the pool of not manually labeled segments to find a segment where the classifier is least certain, and to find segments where the classifier is very certain. And again, the classifier is retrained, and so on. The classifier that we train is the neural network depicted in this picture. The input it receives is the embedding of a segment. Specifically, we employ the pre-trained neural network by Kong et al., which provides the so-called PANN embedding. The classifier consists of a dropout layer, a dense layer, and a softmax layer, and outputs a class probability distribution for that sound segment. Notice how the output of the classifier is randomized, because we employ the dropout layer. Depending on which dropout mask we randomly select, meaning which neuron activations we randomly replace with zeros, the output will be different. Sampling a dropout mask and computing the output can be understood as sampling and evaluating a hypothesis about the relation between the input and the class label. This technique is known as Monte-Carlo Dropout. The final prediction is computed by averaging over individual distributions and finding the class with the highest predicted probability. Furthermore, one can measure the disagreement between individual hypotheses by letting each hypothesis produce a vote in favor of one class. We count the votes of individual hypotheses and compute the vote distribution. By measuring the entropy of that vote distribution, we effectively measure the disagreement between individual hypotheses. We then find the segment where individual votes disagree most. This segment we consider the most informative and pass it to the human annotator to obtain the ground truth label. Now let us look at some results. We evaluated the performance of our active learning system together with two reference benchmark systems on the UrbanSound 8K dataset. What we see here is the classification accuracy plotted against different amounts of manual annotations. The manual annotations are produced by a simulated human annotator. The blue curve shows the performance of a reference method by Shuyang et al., which we use as a benchmark. The orange line is our modification of the reference method, which has been modified to work with PANN embeddings, which, as we see, greatly improves the performance. Finally, the green line is our method, DAL. We see that for low numbers of annotated segments, our method outperforms both reference benchmarks, meaning that our method is most label efficient in this regime. With this, I would like to conclude this brief overview, and if you want to hear more details about the active learning system, as well as more simulations regarding the selection of pseudolabels and the training process, I invite you to join the poster session number 53. Thank you.